So the question or the topic for this section comes from our chapter 7, from our 17 of our textbook, looking at aromatic structures, and in particular benzene. Benzene happens to be the classic aromatic compound. So really what we're going to evaluate in this discussion is what makes something aromatic. Okay? And again, that's what makes benzene special. So if we take a look at the energy diagram here, this is a common kind of question that could get phrased off of the ECS exam. So what we're looking at here is what's known as the heat of hydrogenation. So what we are adding is hydrogen to a double bond. So it's an addition reaction, and we're replacing a double bond with hydrogen. As we add double bonds, we expect a higher and higher, or lower depending on your perspective, heat of hydrogenation. So more energy is released in the process of this hydrogenation, and that's because we have more pi bonds, and pi bonds are higher in energy. So we could go through and evaluate and predict what would happen as we add more and more pi bonds. So 1 pi bond, and we have negative 120, 2 pi bonds. It doesn't scale perfectly because we expect some stabilization due to the conjugation of those pi bonds. So instead of it being negative 240 kilojoules, we get negative 232. As we scale even further up, we might predict effectively 3 times that distance. We're looking at 360 kilojoules per mole as we add the double bonds in. So that's our expected result. Someone went through and actually tested this, and what they found was that it's actually 208 kilojoules per mole. So this is a pretty significant difference between those heats of hydrogenation. So then, of course, the next question becomes is why? Our theory of just adding pi bonds and increasing in energy infinitely doesn't seem to work out, so we have to come up with a new explanation. That explanation has to do with the pi bonds in the benzene structure being stabilized through resonance. So we can draw out a resonance structure where the pi bonds have merely shifted into different positions, and in this case we've now got 2 structures representing the same thing. So the overall energy drastically drops due to this resonance. In other circumstances, for example, someone might say, well, I've got resonance with this pi bond as well, right, with just our standard cyclohexene. And you're right, there is resonance. However, is it good resonance? No, we've got charges, whereas in the case of our benzene, our second resonance structure does not generate any charge. Okay, so it is much more stable because of that. Okay, so that's that stability that we're trying to draw some conclusions from. So benzene is a fully conjugated cyclic compound, meaning all of the pi bonds within the ring can do resonance with each other, or conjugated. And then further, because it's cyclic, it can feed back on itself, and we can negate potential positive and negative charges that we would have seen if this was just a straight chain. Okay, so these are our 2 characteristic features of benzene. So now that we've found a molecule that does this, perhaps we'd like to find some others. Okay? So some examples. Benzene, due to the stabilization, we don't see standard addition reactions that we would see with an alkene, and we don't see our Diels-Alder reaction that we also would expect to see with alkenes, or even dienes, which benzene technically is a triene. Further, if we take a look at the cyclopropenyl cation, the guy on the far right, we notice that we also don't get a Diels-Alder reaction, and addition reactions don't seem to work well. Okay, so we do have something that's similar to benzene. It is cyclic, we do have these kind of p orbitals, and it also doesn't react the same. If we go through and scale with 2 pi bonds, so in this case we move to cyclobutadiene, it turns out that cyclobutadiene will undergo Diels-Alder reactions. Whoops, revealed too much. It will undergo a Diels-Alder reaction. We'll take the diene reacting with our dienophile, and we can end up doing a cyclization reaction, okay, or a Diels-Alder reaction. So cyclic structure, still pi bonds, but it does react under Diels-Alder conditions. We could go through and move to a larger ring structure. So in this case, we've got octatetraene, so 8 carbons and 4 double bonds. And we reacted under addition reactions, and we notice that we do see a result here as well. Okay, so something odd is happening, and this is what, pretty sure it was Huckel's the one that's responsible for this, noticed and started to pick up these patterns and kept coming up with different structures, cyclic structures, and evaluated their stability and their reactivities. And he started to come up with some theories and parallels that he drew out of this. So one of those things that we might notice, if we're going to attempt to do this, is that we notice in the case of our 2 non-reactive, we have 1 pi bond and 3 pi bonds. In the cases of our reactive, it was 2 pi bonds and 4 pi bonds. So, an interesting conclusion. If we have an odd number of pi bonds, we don't have a reaction. If we have an even number of pi bonds, we do get reactions, or we do get this addition type reaction. So Huckel started to postulate and come together with possible theories out of this. And those theories are summarized at the bottom here. Decided to classify these compounds as aromatic. Okay, so aromatic compounds will fulfill these 2 criteria. Number 1, it has to be a conjugated ring. So we're looking at overlapping p orbitals throughout a ring structure. Okay? The next part is that it must meet Huckel's rule. So Huckel's rule is that we have an odd number of electron pairs, which we just kind of went through. That was the 1, 3, 2, 4. Another option that we could go through with this is this formula 4n plus 2 pi electrons. Okay, so looking at electron pairs can be difficult, and I will throw in a kind of a wrinkle of a question in a little bit that makes or helps us clarify what's going on with this. So when we're looking at our pi electrons, we want to count all of the electrons in the pi system. So for benzene, there was 1 electron per carbon contributing to the pi system. So we have 6 pi electrons. If we go to our formula, does 6 pi equal 4n plus 2? What would n be? Well, hopefully you can see that we could solve for n equal to 1. So this meets Huckel's rule. If we go through and take a look at our cyclopropenol cation, we have 2 pi electrons, 1, 2, and the cation supplies nothing. It's a positive charge, so it's only 2 pi electrons. 4n plus 2, where n solves out as 0. What happens in the case of our butadiene? Okay, well, we've got 1, 2, 3, 4 pi electrons. Does this equal 4n plus 2? When we go through and solve this, to get this to work, n would have to be a half. Okay, so Huckel's rule states that n must be an integer for it to be aromatic. So when we solve for the case of our butadiene, we get n equaling a half, which does not satisfy Huckel's rule. So Huckel's is invalid, which means our butadiene is, and we'll run into a definition issue here, not an aromatic compound. Okay. If we attempt this yet again with our last example, our octatetraene, we've got 2, 4, 6, 8 pi electrons. 8 equals 4n plus 2. N would have to be, I can do math not very well, 3 halves. Good, I did that math. Again, not a whole number integer. So again, Huckel's rule is invalid. That compound is not aromatic. Okay? So really we're using this rule to do something or predict something about the chemistry of these molecules. If we find out that it is an aromatic compound, we don't expect addition reactions, and we don't expect Diels-Alder, which is specific addition reaction. If it is aromatic, or sorry, if it's not aromatic, we would expect those possible reactions to occur. So we can do some kind of predictive ability about what the end result is in each of these situations. Okay? So this comes back to then why. So what can we do to predict each of these things? Okay, and this can be done using molecular orbital theory. I know, everybody's favorite. So what we've got here are the molecular orbitals for cyclobutadiene and cyclohexatriene, also known as benzene. Okay, so we draw out our structures. We've got our cyclobutadiene, and we have our benzene. What we're concerned about is the reactivity of the pi electrons. So we're going to look at the molecular orbitals that are made from the p orbitals from the atomic situations. Okay? If we go through and process this, and we're really good with molecular orbitals, what we end up finding out is that for the cyclobutadiene, we have 4 molecular orbitals, where 2 of those possible orbitals have the same energy. Okay, so they are degenerate. We have orbitals of the exact same energy in this state. Okay, those orbitals are referred to as, I can't spell degenerate, degenerate, okay, because 2 orbitals are represented at the same energy level. Okay, so let's go through and clean that up again. So if we could decide now to go through and address the molecular orbitals, or the electrons that would go into this, we now start to add our electrons. Well, in the case of cyclobutadiene, how many electrons do we need to add? Well, each of those p orbitals contributes a single electron. So we're trying to put 4 electrons into our molecular orbitals. So we'll start putting our electrons at the lowest energy, okay, and we will pair before we move up in energy. Okay. Now we put in the 3rd electron, and now the 4th electron. Where should the 4th electron go? Do I pair it, or do I leave it unpaired? All right, it's a little bit tricky, but hopefully you remember, I believe it's the Pauli exclusion principle from your 151. When we have an equal energy orbital, we leave unpaired first, then we pair. So pair only as a last resort within an energy level. Okay, so that's our molecular orbital picture for cyclobutadiene. How about for the cyclohexatriene, or our benzene? We could again go through and evaluate where our electrons are. We should bring in 6 electrons. We'll again go into our our molecular orbital situation, and we slowly start to fill through. Sorry, let me erase that and ask the question. We left them unpaired at first, but now we've got to put in the 5th electron. The 5th electron is now going to have to be paired, because otherwise I'd have to go into a higher energy orbital. So I'll pair first, and then my 6th. Okay? So now the question becomes, why is the structure on the right so stable and the structure on the left so unstable? Well, an analogy that we could draw back to our addition reactions, we saw BH3. And one of the things that was particularly nice and reactive about BH3 is that it was sp2 hybridized, which meant that there was an empty p orbital. So what could we put in that empty p orbital? Well, we could put the electrons of an alkene into it. So if we've got a space to put electrons, we can dump electrons in it from an outside source. So use that information to go through and now look at the molecular orbitals of our cyclobutadiene and our cyclohexatriene. Well, in the hexatriene, we've got all these paired orbitals. There isn't really a nice place to dump electrons. We could go higher in energy, but if we go higher in energy, we're then moving higher in energy, and that's unstable. Okay? And I'm going to add an extra tier on this in just a second. If we go through and take a look at our cyclobutadiene, we have these empty holes. Those empty holes can accept electrons into them. Right? Yes, we do end up pairing them, but we've got a place to put them. We can actually pair things with these electrons. That then increases, well, not necessarily increases, but increases the reactivity of the cyclobutadiene. Okay, so using molecular orbital theory can allow us to kind of predict something about the reactivity of each of these structures. If we went through and tried it with the cyclopropenyl cation, what we'd end up finding out is that we would end up with a molecular orbital diagram. I'll go through and erase everything and draw this one right in the middle. Our cyclopropenyl cation would look something along these lines with 2 pi electrons. There we go. Again, no unpaired electrons, meaning there isn't really anything that's willing to react. Our structure is super stable, compact, ready to be on its own. Okay? So if we have unpaired electrons in our molecular orbital diagram, then we've got a higher energy molecule, which makes it more reactive. If we have all paired electrons, then we don't worry about it. That molecule is going to be relatively stable, which means lower in overall energy, and we predict no reactivity. Okay, so we've got a couple ways that we could go through and look at it. And if this confuses you, that's fine. We have the rules on that previous slide, start at the bottom there, to tell us what makes it aromatic and what doesn't. Okay? You'll notice that when I went through and did this, that I already had some kind of lines drawn up for the cyclobutadiene and the cyclohexatriene. And I also drew the molecular orbital diagram for the cyclopropenyl cation very, very, very fast. So you might ask, how could I do it that fast? Well, somebody else went through and did enough of these things that started to notice a pattern. That pattern is elucidated here. Okay, so I believe the guy's last name was actually Frost, and he was able to note that what we're pretty much doing when we go through and draw out these molecular orbitals is drawing what he termed a Frost circle. So if we want to predict the molecular orbitals, we don't have to go through and do the hardcore mathematics or even draw out all the lobes and nodes and match everything up. What we can do is inscribe the shape of our molecule within a circle and adjust everything accordingly. Okay? So our first step, we get the circle, then inscribe the polygon, so the structure we're trying to determine if it's aromatic or not, with the point at the bottom of the circle. The point has to be at the bottom of the circle because there's only going to be one possible way that we can get all of our p orbitals to overlap, right? So our point will always be the lowest. Okay, we won't have duplication at that end. We can then draw orbitals for more molecular orbital lines for each of the points around the rest of the circle. Okay? At that point, we now really have the basics of our molecular orbital diagram. Officially, through the dead center of our circle is the non-bonding line. So any lines underneath that, or any orbitals, would be bonding orbitals. Any orbitals above that line would be anti-bonding orbitals. So if we take a step back, if we have our cyclobutene here, we've got our non-bonding line running through the middle. So we only have one orbital that is bonding in the cyclobutadiene. What happens with our cyclo, or with our benzene? Well, halfway through runs here, we have 3 orbitals that are bonding, okay, and no non-bonding, or even anti-bonding. So anti-bonding would be above that line. So we have yet another way to go through and look at this. All of the orbitals in our cyclohexatriene or our benzene are bonding type, and if we look at the orbital diagram for our cyclobutadiene, 2 orbitals are in this non-bonding situation. So we've increased the overall energy outside of the bonding section of our diagram. Okay, kind of neat. Again, not a huge issue. We can go through with some of the rules that we've pulled out of it and not have to stress too much about it. Okay, at most I might ask you to draw one molecular orbital diagram for some structure, maybe cycloheptatriene or something like that, so that I can see that you at least have some cursory understanding of drawing these frost circles. Okay, it's relatively simple and straightforward. Draw the circle, put your polygon inside it, put lines wherever the points are. You now have your molecular orbital diagram. Okay, so try to not spend too much time freaking out about it. Just kind of accept it, roll with it. It'll work better. Okay. Where we really want to be careful now is this section, identifying if a structure is aromatic or not. Okay. This is really, really, really key. So we've got to be careful thinking about this. And if you want to, you could draw frost circles for all of these, but it's going to be way more trouble than it's worth. So we can go through and evaluate each of these according to aromatic, or what we'll call for the moment, quote unquote, not aromatic. We're going to adjust those rules in just a second. Okay, so go ahead and pause the video, attempt to decide if these are aromatic or not, and then we'll go through and work them together in 3, 2, 1. So, starting it off, hopefully you got it figured out that our first one is aromatic. Okay, rule number 1 is a conjugated ring. So we have a ring. We have pi bonds that alternate around that ring, so they're conjugated. So rule 1 is satisfied. So we'll do 1, check. Rule 2, we need to satisfy that we have 4n plus 2 total pi electrons. Well, there are 6 pi electrons. This means that n equals 1. This also checks. Okay, so we've got an aromatic structure. Our cyclobutadiene, if we go through and take a look at this, 1 checks out because we do have a cyclic structure and we have alternating pi bonds around the structure. So pi bond sigma, pi bond sigma. Okay, so that checks out. Rule 2, we have 4 pi electrons, which says that n is equal to 1/2. This does not check out. Okay, so that means, and this is where we're going to run into some new terms here in just a second, not aromatic for the moment. Okay, I will change that in just a second. Okay, so let's move to the next question. Number 1. Fully conjugated ring with overlapping p orbitals. Well, I do have pi bond, sigma, pi bond, but then I go sigma, sigma. Okay, so sigma, sigma, pi, sigma, pi. This structure is not fully conjugated. Okay, because it's not fully conjugated, rule 2 fails. So I guess we'll use x's. Okay, which we would then potentially classify as not aromatic again. Okay, and this is where our rules get a little bit weird. If we take a look at the orange versus the blue, both of those failed Huckel's aromatic test, but they failed different rules of Huckel's test. The big clutch one happens to be number 1. Okay, a fully conjugated ring with overlapping p orbitals. Officially, we're going to see another rule pop in here that will qualify for rule number 2, but because they have different error rates or fail rates with this rule system, we come up calling them different things. Okay, the orange one stays not aromatic. However, our blue one gets a different name. It becomes anti-aromatic. Okay, I know that's a little bit weird, so we've got 3 terms that we've got to be able to control and manipulate here. Aromatic, anti-aromatic, and not aromatic. So not aromatic, no conjugation, period. That's done with. Anti-aromatic is going to fall under a slightly different set of pi electrons, which we'll look at in a second. It has to satisfy a different rule. Okay? So let's go through with the rest of these. Our next one, let's see if I can color code this right. We're going to be looking at rule number 1. We've got a conjugated system. This one's a little bit weird because we do have pi, sigma, sigma, but the hybridization of that middle carbon is sp2, meaning there is an empty p orbital there, that p orbital, through resonance, can overlap with the pi bonds of our other system. So this means we do have a conjugated ring with overlapping p orbitals. Okay, so rule number 1 is indeed satisfied. Rule number 2, the pi electrons involved in it. Well, our cation, that positive charge, is an empty p orbital, meaning it brings in no electrons. So the only electrons we've got here come from the pi bonds, which is 4 pi electrons. 4 pi does not satisfy our rule, and we end up looking at anti-aromatic. We move to the next structure. Okay. Rule number 1, we need to have a conjugated ring with overlapping p orbitals. Well, we do have conjugated p orbitals and pi bonds, but it's not a ring. Rule 1 fails immediately, not aromatic. Okay. Next one. Rule number 1. Okay. Conjugated ring. So we do have a ring. We do have these pi bonds that are conjugated, but what's going on with the oxygen? Well, that oxygen has lone pair electrons that we can draw resonance to push those pi electrons, or push the lone pair electrons into the ring. Okay? Those of you having trouble seeing this, I highly recommend a model kit for this. Okay? And I can show you that if you talk to me during office hours. So what ends up happening with that structure? We do have the ring, and we do have conjugation throughout the whole thing. It does satisfy rule number 1, even though we don't officially have a p orbital on that oxygen. Very, very tricky. Okay? The hybrid orbital holding the lone pair, that sp3, can bend up into the plane and act as a p orbital, which then brings us to the next point. Okay? If we can bring those those sp2 lone pair electrons into a p orbital, then those 2 electrons are part of the pi system, and we end up with now 6 pi electrons. 6 pi electrons puts us at aromatic. Tricky, but we have to watch out for that resonance effect. If you can draw resonance, you're good. Then we move to the last one. This one gets even more fun because it gets back to all of these concepts again. Any guesses on what our answer is going to be? Rule number 1, do we have a fully conjugated ring with overlapping p orbitals? We notice that we do have the pi bonds. Okay, so that's a good sign. And we also have a lone pair on the nitrogen, just like we had on the oxygen. Okay? Well, we also have a lone pair on the other nitrogen. And this is where we're going to have to be careful. I can draw an arrow like this and pretend that's resonance. Okay? But as you might be able to guess based on me calling it pretending, that does not count as resonance. And that is because the lone pair is in an orthogonal orbital to the pi system. Okay? That nitrogen has its p orbitals currently coming in and out of the plane of the screen at you. If we take a look at the lone pair, it is in the plane of the screen. That means they're in opposite locations. If I try and rotate this structure and pull this up out at you so that it can shift into the plane, what happens to the p orbital that was making the pi bond? Well, then that rotates out of the plane and is no longer part of the pi system. Okay? So the lone pair on that nitrogen does not count as part of resonance. Okay, but what about the other nitrogen? Well, it's in the exact same situation that we had with the oxygen. We have an atom that is sp3 hybridized. We can do a very slight rotation of that sp3 bond angle to drop it into the plane of our p orbitals coming in and out of the plane of the board. and those electrons do contribute. So we end up with a conjugated system. Again, tricky. A model kit makes it a lot more apparent as to how this works. Rule number 2, how many pi electrons? Well, we just counted them out. We've got the 4 electrons coming from our double bonds. From our top nitrogen, we can count the lone pair. From the bottom nitrogen, we can't count it. Okay, so that gets us a total of 6 pi electrons. This guy is aromatic. Okay. Some of those were more challenging than others. Ultimately, in each of these cases, it's applying the rules. So with aromaticity, it's kind of like nomenclature. You have to know the rule. You apply the rule, you're golden. You don't know the rule, then you get the answer wrong. Okay? So, before we look at that one, here's our summary of our rules. So our aromatic, we've seen pop up. You'll notice that I've added an extra little kind of caveat on this. That line here, a p orbital can be generated through resonance, which is what we saw in the case of our oxygen and our nitrogen. The lone pair on that oxygen can push resonance in. Okay? For a class that might be more concerned about just memorizing the rules, one lone pair on sp3 atoms counts. If the atom is not sp3 hybridized, you can't count the lone pair. Okay, so in the case of this oxygen, it is sp3 hybridized because we've got the 4 groups of electrons. We can count 1 pair of electrons into our total system. Okay? If we shifted it to the nitrogen example, let's just go ahead and stick with the same example we were looking at here. The nitrogen that's in the bottom of that, now our purple nitrogen, has an sp2 hybridization, which means I can't count the lone pair. Okay? So you can memorize this sp3 rule to help you qualify if the electrons count to it. Once we know what electrons there are, then we can go in and satisfy Huckel's rule. And we're looking for that odd number of electron pairs. The anti-aromatic rule we kind of left off as saying it was just any pseudo-aromatic structure that didn't satisfy Huckel's rule. It's a little bit stricter than that. Okay? For an anti-aromatic compound, it does have to satisfy 2 criteria. It has to have a fully conjugated ring, okay, which we did mention already, but we're looking at an even number of electron pairs, or 4n total pi electrons, okay, where n is your integers in that case. Okay, so we have a new equation for it to fit in. In most circumstances, if you find a structure that looks aromatic because it has the fully conjugated overlapping p orbitals but doesn't meet Huckel's rule, it's probably anti-aromatic. Okay? Yes, exceptions can be thrown at you, but for the most part, you could probably just guess it's anti-aromatic. In the case of the non-aromatic, it invalidates rule pretty much number 1. Okay? Something's wrong right off the bat. Okay? Either we don't have conjugated double bonds, or it's not a ring. Okay? So a lot of structures are non-aromatic. You can see a trick question pop up. I thought I'd shrunk the font size down on that. If a structure looks like it's anti-aromatic, because the anti-aromatic structure is unstable, it can tweak its geometry so that it is no longer a fully conjugated system with overlapping p orbitals. Well, if that rule becomes invalid, then it's not anti-aromatic anymore, it's non-aromatic. It is a very subtle tweak to the rules. I won't ever ask you a question like that. The ACS exam doesn't ask you a question like that. And I'm pretty sure the Smith textbook that we're using doesn't throw questions at you like that either. And I know for sure the homework doesn't. I verified all the homework questions. Okay? So that's our overall summary for the rules. So if we go back to the previous slide and take a look at that last structure. Okay, we're going to again do kind of a pseudo countdown. Let's have you go through and pause it and decide what you think this structure is, aromatic, anti-aromatic, or non-aromatic, and we will start with the answer in 3, 2, 1. Going through with our structure, we do have a cyclic structure. Okay. As far as overlapping p orbitals, well, this carbon is sp2 hybridized, sp2, 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 so we do have p orbitals all the way around this that could potentially overlap. So rule number 1 is valid. Okay, it does check out with that. Okay, so we do have a cyclic structure, and we do have p orbitals that can all be conjugated with each other, so we get this planar structure. Here's where this comes in really tricky. Rule number 2. How many pi electrons are in this system? Okay, and again, I'll give you a couple seconds here to think about this, and we'll go with 3, 2, 1. Pi electron, pi electron, pi electron, pi electron. For sure, those 4 are in the pi system. I completely agree. Now we run into the next issue. If we take a look at the carbonyls, there's a pi electron on the carbon and a pi electron on the oxygen in both circumstances. Okay. If I count all of the pi electrons in this structure, I get, sorry for the pause, slow adding, 8 pi electrons. So the structure has 8 pi electrons. Okay. So you notice I've got that caveat of the structure. If I went through and drew out this deal, so that's a benzene with big long chain on it and a double bond. Is that structure aromatic? Well, yeah, when we look at this, it's aromatic right there. Okay. Did we count those pi electrons to determine if it was aromatic? No, because those aren't part of the cyclic conjugated system. So when we go through and take a look at our problem, yes, the structure has 8 pi electrons, but of those pi electrons, which ones count towards the cyclic conjugated system? The only ones that count are in here, which means I have 6 pi electrons. Since rule 1 and rule 2 are valid, we're looking at an aromatic structure. Tricky. Okay? So just because you see a pi bond does not mean you can count it as 2 electrons being part of the system. You have to be very, very careful with what electrons get counted in your total. They must be part of the cyclic structure or the cyclic system. So again, our summary of rules. So then what do we do with this? Okay, so there's a couple things that come out of why do we care about aromaticity. Number 1, we started off right away. Aromatic structures are incredibly stable. Okay, that's a big benefit, but that's a big thing that comes out of them. They do not react like alkenes because alkenes are more reactive or higher energy than our aromatic rings, which means if I want to get an aromatic ring to react, I'm going to have to do some new chemistry that we haven't seen before. Okay, and that's what chapter 18 in our textbook is all about. Okay, the next thing that we could also go through and do is use our understanding of aromatic versus anti-aromatic or non-aromatic to actually do some predictions about reactivities of molecules. Okay, so if we take a look at pyridine versus pyrrole, very similar structures, and in fact both of these are aromatic compounds, okay, at least at this stage. And we could figure that out by going through and being a little bit more careful with how these are drawn and looking at the lone pairs on each of these. In pyridine, the lone pair on our nitrogen does not count because that's an sp2 nitrogen, so out of the question. we get our 6 pi electrons, we have an aromatic structure. So aromatic. If we take a look at the pyrrole, we've got our pi bonds and sp3 nitrogen, but it does have a lone pair. I can count that lone pair into my total. So again, I've got 6 pi electrons. This structure is also aromatic. Okay. If I want to now look at the reactivity of these two structures, okay, it's really going to come down to the same general thing in both cases. It is centering around the nitrogen, and in particular, the lone pair on the nitrogen. Okay. The pi bonds won't react very easily because they're involved in the aromatic structure. So we don't have to worry about the alkenes. What we need to look at are the lone pairs on those nitrogens. Okay. As we've alluded to in first semester, and we've started to allude to this semester, and we'll see at the very end of the semester, nitrogen typically acts as a base. Okay. And when we say base, we mean a Bronsted-Lowry base. So if I'm going to look at the reactivity of these two, I'm going to tell you that both of these compounds are basic, are Bronsted-Lowry or potentially Bronsted-Lowry bases. Which of these compounds is more basic? So which one's the stronger base? I'll give you a second to again think about this one before we start revealing the answers. We'll come back in 3, 2, 1. To do that, we should draw individual reactions where we have them act as a base. Have them remove the hydrogen from some unknown acid, we don't care what the acid is, and look at the result. What happened to our nitrogen compound? Okay, and since I don't know, okay, I don't want to reveal that yet, sorry, come back. Let's go through and use our understanding of aromaticity. To start with, we said both of our compounds were aromatic. Aromatic and aromatic. What happens after they act as a base? Well, in the case of our pyridine, we still have our 6 pi electrons. We're still aromatic. What happens in the case of our pyrrole? When we get to the pyrrole, we've lost the lone pair. Okay? Even further, we now also don't have a p orbital on the nitrogen. Okay, that nitrogen has now become sp3 hybridized. There's no p orbital even remotely possible for the conjugated system, which means what we now have on that nitrogen, or in the case of the pyrrole, is now a non-aromatic species. And why is that important? Well, what did we say about aromatic structures? They're incredibly stable. So if I look at the reaction where I start aromatic and go non-aromatic, is that a favored thing to do? No, it's a horrible idea. We started stable and now we made it ridiculously unstable. That's a bad idea. So we can see that in the arrow given to us. Okay? Pyrrole will not act as a good base because it becomes non-aromatic. So if I want to use a basic compound, I'm going to use pyridine. Okay? And why would pyridine not really care? Well, it started aromatic and it became aromatic. So nothing really changed. Yes, we do see this charge issue show up, and yes, that's going to contribute to our stability, but there isn't a larger effect. It's really just this aromatic versus aromatic thing. Nothing really changes. Our pyridine will act as a base. To prove this, we could go through and look at the pKa's of our acids. The smaller the pKa, the more acidic the compound. When we take a look at the conjugate acid pyrrole, our pKa is really, really low, 0.4. So we're looking at something really, really acidic. Whereas the pKa for our pyridine, again, it is relatively low, but it's nowhere near as low. Okay? On the pKa scale, we're going by, oh crap, I think it's factors, it's either 10 or 100. Okay? I think it's, I don't remember, let's call it tens. So to go from approximately 0 to 5, we're looking at a 500-fold difference in acidity. Okay? That's a pretty drastic difference in the overall reactivities. So if we can look at a structure and say, ah, that structure is aromatic, or ah, if I do this one step, the structure becomes aromatic, that's going to start to contribute to our overall guessing on what reactions are going to happen. Okay? So it's really the goal behind all these definitions of what is aromatic and what is not aromatic. Okay? So I really thought there was another slide there. Unfortunately, there's not, so we can move into the spectroscopy of our aromatic compounds. So if we drew out a benzene, come on, we drew out a benzene, which I'll drop in the no real space upper left-hand corner. We've got a lot of carbons and hydrogens within that structure. So we've got the carbon-hydrogen stretching from an sp2 carbon. Should stand out just above 3,000, but an alkene could do the same thing. We also have the carbon-carbon double bonds. Okay, so we've got our CHsP2. We also have the carbon-carbon double bonds, which show up in 1450 to the 1650 range. Our alkenes show up about 1650, so we could, in theory, look in that range and determine that we have an aromatic compound by seeing some more characteristic stretches. So those two signals you should already know from the IR. The ones that are new to you are going to be the 1700 to 2000, the 1000 to 1275, and the 690 to 900. Okay? There's a decent amount of information to be found there, but all of those signals are relatively weak, and there's a lot of other stuff that can show up in those ranges. So they become a little bit dicier to analyze. Okay, so it's kind of up to you. Our next slide here kind of shows those ranges. We've got the 900 to 600 range shown first. I pulled this slide from the internet, so don't blame me on the order. To our 600 range. And we have our 200 to 1600 range. Or sorry, 2000 to 1600 range. So what they're trying to show in each of these cases is if we change the structure of our benzene, we expect very particular patterns to show up in our IR. So in the case of a monosubstituted benzene, whoops, didn't mean to draw through that, we would expect to see two strong signals show up in that 900 to 700 range. One probably about 750 and one about 700. Okay? You'll notice there is some overlap. The meta substitution, okay, which we'll talk about what that means as well, has similar peak patternings. So it is very difficult to go through and analyze that range, but if you spend a little time practicing, looking at a whole bunch of different aromatic substitution patterns, you can start to pick up these patterns and recognize relatively quickly what you're looking at. Same deal for your 2000 to 1600 range. Okay? So they've gone through and explained what each of or state what these are. So monosubstituted, meaning a single hydrogen on that ring has been replaced by anything other than a hydrogen. You end up seeing this peak patterning in that 2000 to 1600 range. Okay? There's a lot of other stuff there, so it does tend to get overwhelmed and you may not see it. That's why it's tricky, and that's why we don't typically talk about it until now when we're looking at aromatic compounds. Okay, so take a look at some of the spectroscopy in your textbook and look at those ranges and see if you can kind of get a feel for it. Okay? Not an urgent thing to do. It can be a helpful tool if you spend the time to play around with it. If you don't want to spend the time, then that's your call. Rely on other things. Spectroscopy for your aromatic compounds. If you have an aromatic compound in your spectra, you should be really happy because they stand out fairly quickly. If you do your unsaturations, you get a lot of unsaturation for a ring, 4 degrees of unsaturation. So if you have a degree of unsaturation that's 4 or higher, there's a really high likelihood that you're looking at an aromatic ring. Okay? Beyond that, there's only so many different ways you can arrange things around an aromatic ring because there's only 6 locations that are possible to interchange. So we could go through and draw out all the possible ways to put different items on a ring structure. And once we have all of those possible options, we can then go through and predict what we would expect to see in the carbon NMR and the hydrogen NMR. I got this slide from the Klein textbook, and they seem to really like the use of the carbon NMR. Can't say I'm a big fan of it because that range also overlaps with alkenes. So you could be seeing misleading information thinking you're looking at an aromatic, but you're actually looking at an alkene. So be careful interpreting your carbon NMR too excessively, but you can pick up some useful information from the carbon NMR for aromatic rings. The other option can be done for HNMR. So I personally like the HNMR option better because aromatics in the HNMR show up where? Okay, everybody should have it memorized. Your aromatic structures for HNMR show up in the roughly 6.5 to 8.5 ppms, usually centered around 7, okay, or mid-7s. Alkenes don't show up that high, okay, largely due because of extra features within the aromatic ring. So that means if I see signals in that range, I know it's aromatic. I can go through and start to analyze the aromatic range and nail down my structure pretty quickly. Okay. Classic example is the case we've got here. This is what's known as para substitution. Okay. Para is really just saying that we have a 1, 2, 3, 4. So we have things at position 1 and position 4 on an aromatic ring. That's all that means. So para equals 1, 4 substitution. Okay. If this were the case, and we draw on our hydrogens, number 1, we have symmetry running through the middle of our molecule. So the hydrogens on the opposite side are the same. So we can call it purple hydrogens are identical to each other versus the blue hydrogens. So we really only end up with 2 signals in our HNMR. The next part is what would our splitting pattern look like, our multiplicity. Well, to do that we could look at our neighbors. We've got 1, 2, 3 bonds away, 1 neighbor. We could try and count other distances out. 1, 2, 3, not a hydrogen, or 3, not a hydrogen. There's only 1 neighbor from our hydrogen, which means we'd expect a doublet. Our blue hydrogen, we expect the same result, and what we end up seeing in our HNMR, somewhere in that 7 range, is 2 doublets. Okay, very characteristic, jumps right out of the paper, screams at you, I have a para-substituted aromatic structure. Okay. What I would recommend that you go try and go through and do on your own time, and feel free to check with me if you would like, is pick another structure. Let me not draw there. Go ahead and put an X on there and an X over there. What's the result in this case? How many signals would you expect? Right? So instead of memorizing all the chemical shifts and all these things that could possibly come out of these, with the aromatic structures, if you think there's one there, start guessing and match that to what you see. If it's not what you see, then that can't be the correct substitution pattern. So it can allow you to simplify your answers down a little bit. Okay? Again, practice makes perfect when it comes to spectroscopy. If you clear roughly 50-60 hours worth of spectroscopy, you should be able to crunch through a spectral problem in under a minute probably. Maybe under 2 minutes if you had a little bit of a rough time with those 50 hours. Okay, so your first problem, hour to 2 hours to solve one problem. 50 hours worth of work, you're solving it in under a minute. So to me, there's a big reward for spending the time to learn spectroscopy because you can get those answers pretty much instantly. Okay. That covers everything that I wanted to cover within our mixed lecture. I do want to hit one more slide, which we will see in class again. This lecture is getting posted here shortly. Here's the last slide, foreshadowing into Chapter 18. our big lesson from this lecture, benzene is incredibly stable and low energy, which means anything that we can do to make benzene is a good thing. It's going to be a very high energy payout. We're going to form that structure as quickly as possible. Okay? Which also means it's not easy to get benzene to react in the first place. So we have to use special reagents to kind of activate it and get it to go. As kind of our foreshadowing, what might be the expected chemistry for this following molecule, and because you are going to see it in lecture, go ahead and just draw it out. This molecule is actually quite acidic, because if I take the electrons away from that hydrogen, I end up with benzene, okay, and the H plus floating off on its own. If we make the benzene, that is a very high payout reaction. That step is very, very fast because we're trying to reform that very low energy state. Okay? As always, if you got questions, send me an email, grab me in class, that kind of fun thing, or office hours. And I will see you on Wednesday.